Hi, Dr. Pitcher here again, and in this lecture, in Chapter 7, we're going to take a look at the stability of alkenes. Now, let's just take as an example um, the following reaction. So we could have a trans alkene, trans 2-butene, and in the presence of an acid catalyst, H plus, I'll just write cat there for catalyst, we can get an isomerization reaction and end up with the cis butene. Now, if we took a look at this, we would see that the equilibrium actually favors the trans. So another way of saying that is that the trans isomer is more stable. So in this case, we have a particular reaction that adding a little bit of acid will allow us to allow this isomerization to happen. But often we can't do that. So the way that we get at this is look at what are called heats of hydrogenation. Or delta H. Of hydrogenation. And so essentially what we're doing here is we are taking some alkene, in this case it's our trans 2-butene, we're going to hydrogenate it. And we'll talk about the hydrogenation reaction in the next chapter. We're adding H2, and so we add one hydrogen to each carbon in the double bond, and we get butane. Now, it turns out that we could do the same thing with the cis 2-butene, and we get the same product. So we can look at delta H for this reaction, and we would see that our delta H for trans and our delta H for cis are just a little bit different. Our delta H for trans is, and I've got this nifty table here, it's around 115 or 116. Actually, you can see here the table says down there 115 for trans, but the figure here says minus 116. So we'll go with it with what's in the table. So minus 115 kilojoules per mole. And delta H for the cis is minus 119 kilojoules per mole. So what that means is that, if we were to look at, let's say, a reaction progress diagram, we're ending up at the same place, butane. But we have a larger negative delta H, which is not quite the same as delta G, but it's usually pretty close. And so on this energy diagram, reaction progress diagram, we're calling it delta G. So the cis is higher in energy, so when it gets hydrogenated, more energy is released. So that's why its delta H of hydrogenation is more negative than the delta H of hydrogenation for the trans. So cis is higher in energy than trans. When you do the hydrogenation, which is exothermic, you get a larger release of energy. So we can use this table to come up with a general trend, and this is just table 7.2, and we can come up with a general trend for what these stabilities are. And this is a This trend is one that's worth remembering. So if I'm going to, so we'll look at, we'll say trend in alkene stability. So the trend is that the more substituents you have attached to the double bond, the more stable. So something like tetrasubstituted would be the most stable. So that's going to be more stable than trisubstituted, which is more stable than disubstituted. And now the cis and the trans are not equal. Okay, the cis has is a little less stable, 4 kilojoules per mole less stable than the trans. But trans is actually about as stable as what we call geminal. That is, we've got 2 substituents on the same carbon. So those guys are about the same. And that is more stable than the cis, which is more stable than monosubstituted, which is more stable than the unsubstituted ethylene there. Okay, so the more substituents, the more stable. Now, there's a reason for this, and this reason is due to something called hyperconjugation. Let me write over here, least stable. So this is due to hyperconjugation. And there is a figure in the text, figure 7.7, that shows hyperconjugation. So let me zoom in here just so you guys can see this a little better. And basically, hyperconjugation is an overlap of orbitals. And it's an overlap between a p orbital and another orbital, like, let's say, an sp3 orbital. Orbitals that normally you wouldn't think would overlap. But in this case, there actually can be some overlap. So here we've got overlap that is overlapping p orbitals, and that gives us our pi bond. And then over here we have this sigma bond here. So the sp3 from this carbon and the s orbital from the hydrogen. And that can actually overlap a little bit with the pi system here. And so you get this kind of big blobby molecular orbital. If we were going to try to look at it maybe a slightly different way, let me go ahead and get my model out here. So if we had a series of pi bonds, let me zoom out again here, sorry about that. If we had a series of, let me zoom out one more. Oh, I guess I am zoomed out. Okay, if we had a series of pi bonds interspersed with single bonds, those would be conjugated, regular conjugation, because all the p orbitals could overlap. But when we have a potential overlap between something that's a p orbital and then an orbital that's not a p orbital, so right here, this p orbital could have some overlap with this guy here. Okay, again, these are not quite to scale, but there is an interaction, and that's what's called hyperconjugation. Now, hyperconjugation explains why the more substituted are more stable. So the more of this hyperconjugation, The more you're spreading out electron density, the more overlap you have. And the more spread out the electron density, the lower in energy something is. We'll revisit this again when we look at some reaction mechanisms where we form species called carbocations. And it turns out that hyperconjugation plays a role in the stability of carbocations, as well as the stability of alkenes. All right. Well, that's it for this lecture, kind of a short one, but until next time, stay safe out there. Bye now.